You are standing at the crumbling edge of the modern world. Bridges fall, buildings crack, roads break open with a sigh and collapse like exhausted travelers. Our concrete modern gray efficientivin begins to disintegrate within a few decades. And yet, somewhere on the coast of Italy, battered daily by the sea for over 2,000 years, a Roman pier still stands. How? Let's begin, not with the glory of the Colosseum or the soaring arches of aqueducts, but with something smaller, more ordinary. A broken-down fish dock on the Bay of Naples, Roman, still intact, and made not of stone, but of something we call today, without irony opus cementitium, Roman concrete. It wasn't the first artificial building material in human history. Mud brick and fired brick had existed for millennia, but the Romans did something different. They made their concrete better with age, and the strangest part, it was almost accidental. What is concrete, anyway? You probably know the modern recipe: cement, sand, gravel, water, mix and pour. What we call Portland cement, developed in the 19th century, hardens fast, but deteriorates in seawater. Over time, its structure weakens, salts seep in, steel, rebar rusts. The whole thing eventually turns to powder. Roman concrete was utterly different. It was made with lime calcium oxide, volcanic ash, and aggregate mix of small stones or brick fragments. But the key wasn't just what they used, it was how long they waited. Roman concrete wasn't poured like ours, it was layered, left to cure for weeks, and the ash, not just any dust, it came from places like Pesawali, near modern Naples, where volcanic minerals were rich with silica and alumina. This ash is called pozzolana, and it's still studied today. But the Romans didn't think in chemistry, they thought in qualities. They observed. They noticed that structures built with volcanic ash from Campania fared far better over time, especially in harbors. That's where things get truly strange. 2. Building in water. Before waterproofing, in the 1st century BCE, Rome was booming. Grain shipments, armies, and trade goods all needed better infrastructure. So, Roman engineers, some educated, others just skilled, through generations of practice, began pouring concrete underwater. Yes, underwater. You would think that would weaken the material, but with Roman concrete, the sea didn't destroy, it strengthened. Unlike modern cement, Roman harbor concrete contains crystals that grow over time. As seawater interacts with volcanic minerals, it causes chemical reactions. One of the most crucial, the formation of aluminum tobermorite, a rare, stable mineral. This crystalline structure forms in the crack sand, seals them. In short, the concrete heals itself. No modern civil engineer in the 1800s could explain this. In fact, we didn't start to understand it fully until electron microscopes came into the picture in the 21st century. How did the Romans know? They didn't, not in scientific terms, but they saw the results. Trial and error across hundreds of sites, from the fish ponds of wealthy nobles to imperial shipyards, taught them which mixtures endured. They learned slowly, patiently, across generations, and they recorded very little. 3. Vitruvius and the whisper of formulas. What we know about Roman concrete comes, in part, from Vitruvius, a Roman architect and engineer, writing around 15 BCE. His De Architectura, dedicated to Emperor Augustus, includes advice on everything from acoustics to city planning to concrete. He writes, almost casually, with pozzolana, when it is mixed with lime and rubble, it hardens as well under water as in ordinary buildings. Casual, as if this were not miraculous. Vitruvius does not give us detailed ratios or temperature instructions. His writings are part how-to, part philosophy, and part poetry. In his world, materials had humors. The earth breathed. Lime was alive. A builder was half priest, half technician. Science was observation, not theory. So we don't know exactly how they mixed the concrete, or why certain batches lasted longer. But we do know this: Vitruvius understood the difference between earth ash and mountain ash, and preferred the kind that came from near the sea, rich with marine influence. This intuitive chemistry mattered. For the labor of lime, before you could even mix Roman concrete, you had to make the lime. This was no small task. Workers burned limestone at high heat, often for desousing wood or charcoal. The resulting quicklime calcium oxide was unstable and caustic. Mixed with water, it turned to slaked lime calcium hydroxide, ready to bind with ash. The process was hot, dangerous, and terribly slow. It was also deeply local. Concrete from one region was different from another. The Romans didn't have standardized units, no fixed engineering manuals. They had traditions, recipes passed between guilds. Each region of the empire had its own flavor of concrete. Some lasted, some failed. The most resilient often came from the Italian peninsula, where the marriage between lime and volcanic ash formed the toughest union. And this brings us to the question of why they used it so much in harbors v. The seawall that should have fallen, one of the most astonishing structures from ancient Rome, is the Portus Cosenus breakwater, a massive seawall off the coast of Tuscany, constructed in the 2nd century BCE. It was built with submerged concrete forms, poured into wooden cofferdams. Today, the wood has rotted. The empire has long since fallen, but the concrete still solid. Scientists who sampled the breakwater discovered a unique formation of hydrothermal minerals. The interaction between volcanic ash and seawater caused long-term reactions that actually improved the structure over time. They called it rare and unexpected, but was it? The Romans built dozens of harbors. They saw what survived. They copied it, repeated it, tweaked it. That's the secret ingredient of Roman concrete, not a rare mineral, but centuries of careful imitation. They didn't invent durability in a lab. They observed it over generations. Boring about Roman concrete: it didn't dazzle. It didn't gleam like marble or echo with the clang of bronze. But it held. It endured. Romans knew how to make quick things: brick facades, wooden scaffolding, marble cladding, but concrete was their slow art. It had to sit, breathe, set, strengthen. They accepted waiting. They embraced incompleteness. Some structures took years to cure fully, but they were not designed for a generation. They were meant to outlast emperors, and they often did. As we move forward, you'll see how Roman concrete shaped everything from their sewers to their temples. But first, let's look at the stuff no one notices, the everyday. The places where concrete quietly held life together, from grain stores to latrines. But before we go there, consider this. If Roman concrete became stronger in salt water, what would happen to a Roman bathhouse, a place filled daily with hot, mineral-rich water? Would it weaken the concrete, or would it make it immortal? Immortal. You hear the sound of dripping water echoing through an arched corridor. It's dark, humid, warm. Thermi, but you're not here to bathe. You're here to examine the walls, the floors, the hidden foundations. Why? Because the same material that held up an imperial harbor is also holding together this unassuming, quiet corner of ancient public life. And yet, the bathhouse posed an entirely different challenge for Roman builders: constant heat, moisture, and human wear. The perfect testing ground for Roman concrete. Let's begin at the furnace. Fire under the floors. Most Roman bathhouses used a system called the hypocaust. It was an early form of radiant heating, using a space beneath the floor to circulate hot air. Slaves or workers fed a fire in the prefurnium, usually from outside the main structure. Heat traveled beneath the suspended floors, supported by small columns of bricks called pilae, then rose through terracotta flues embedded in the walls. This meant that the foundations and walls were constantly exposed to temperature fluctuations, stress test for any building material. Modern concrete expands and contracts with heat, causing microcracks and gradual failure. But Roman concrete, curiously, seemed to handle it better. Why? In part, because it lacked steel reinforcement. There was nothing inside to rust. But more importantly, the Romans didn't over-engineer. They let the concrete breathe. You'll notice that many Roman walls are layered not in one solid pour, like our modern slabs. These layers relieved pressure and allowed the structure to expand and settle without breaking apart. But there was another hidden factor: the chemistry of the water itself. Water that strengthens walls. Roman bathhouses didn't use distilled or treated water. They used spring water, sometimes cold, sometimes warm, always mineral-rich. These minerals didn't just affect bathers' skin. They interacted with the walls, floors, and mortar in complex ways. Hot water flowed daily through lead or ceramic pipes, over concrete floors, and against concrete walls, and sometimes invisibly within the pores of the concrete itself. Some modern researchers believe this may have contributed to the long-term strength of Roman bath structures. The constant flow of hot, mineral-laden water may have slowly sealed microscopic cracks, filling voids and preventing internal decay. The very act of using the bathhouse helped preserve it. Imagine a structure where foot traffic, boiling water, and the scraping of sandals didn't wear it down but helped protect it. It's not magic, it's observation over centuries. 3. Pozzolana goes indoors. While Roman harbor concrete is most famous for its durability, similar mixtures were used in land-based architecture, especially bathhouses, cisterns, and aqueducts. In these settings, Romans used a particular formulation of pozzolanic mortar, a blend of volcanic ash and lime designed to resist water infiltration. These mortars didn't set immediately. They cured slowly, forming tight, interlocking crystals over months or years. This was ideal for vaulted ceilings, subterranean chambers, and, of course, hot water basins. Take, for example, the baths of Caracalla, completed in 216 CE. The complex covered over 33 acres and could host thousands of people daily. It had pools, saunas, libraries, gardens, and massive vaulted ceilings. The roofs, over 100 feet high, were supported not by solid stone, but by Roman concrete core faced with bricks. 2 millennia later, parts of those cores still stand. The collapse of the Western Roman Empire didn't bring them down. Bombing during World War II didn't bring them down. And while some outer facades have vanished, the concrete remains, quietly winning a battle against time. 4. The quiet builders. Labor behind the walls. It's tempting to picture Roman engineers in togas, drawing diagrams with elegant compasses. But the reality was more gritty. Roman concrete was mixed on site, often in pits or trenches, using shovels, buckets, and muscle. Lime had to be transported carefully, could spontaneously ignite when wet. Volcanic ash was hauled in carts, sifted, and dumped. Water came from aqueducts or wells, and then the whole thing was stirred by hand. No cement trucks, no electric mixers, just brutal, repetitive labor. And that labor was often done by slaves, indentured workers, or members of building guilds. Under strict contracts, some workers specialized in the foundations, dealing with the deepest, muddiest, least seen part of the structure. Others specialized in vaults, laying bricks in curving arcs to shape the hollow interiors, then pouring concrete behind them to set. They didn't write books. Go to Rome, visit the cistern of Nero, a vaulted underground reservoir lined with waterproof mortar. Walk down into the Cloaca Maxima, Rome's great sewer, where concrete channels still divert water from streets to the Tiber. Or explore the Piscina Mirabilis, a naval cistern near Naples, with 48 vaulted naves of concrete and stone. You will not find plaques. You will not find signatures. But you will find permanence. The architecture of patience. There's a theme that runs through every Roman concrete structure. Time. Roman builders waited. After pouring a layer, they let it sit. After curing, they added another. Large domes, like the Pantheon, were poured in stages, using lighter aggregates near the top pumice instead of stone to reduce weight. Imagine the patience this required. Each step measured in weeks, not hours. Modern concrete aims for speed. We mix, pour, and hope for 28-day strength. Roman concrete was more like gardening. You prepared the ground, you planted, you watched it grow. And because they waited sometimes for years, the final structure settled naturally. It cracked less, it cured evenly, and it became, over time, less vulnerable. The Romans knew boredom. They knew waiting, and their concrete reflects it. Concrete of the mundane. Most Roman buildings weren't spectacular. Yes, the baths of Caracalla or the Colosseum are grand, but most Romans lived in insulae apartment blocks made of concrete cores and brick facing. Lower floors were coveted, upper ones were death traps, and yet the method was the same. Concrete 4 cores, mortar of lime and ash, vaulted ceilings when possible. Builders applied the same basic logic to luxury and poverty alike. Even the latrines, communal toilets, were made with this concrete, vaulted ceilings, drainage channels, a slab with holes and running water underneath. Boring, practical, durable. You won't see many Instagram photos of them. Beneath your feet, still holding firm. 7. The pause before decay. As we close this section, ask yourself, why did this knowledge disappear? Why, after Rome fell, did Europe forget how to make concrete this durable? Why did cathedrals rely on stone? And why did early modern engineers reinvent inferior cement? The answer is, in part, cultural collapse, but also impatience. Roman concrete took too long for the new world. New rulers wanted castles, not sewers. They wanted height, not hygiene. Roman concrete didn't shine. It didn't inspire worship. It just worked. So now you've seen how Roman concrete didn't just build harbors or temples, but also held together daily life, baths, cisterns, latrines, apartments. In our final section, we'll return to the Pantheon, one of the most studied concrete structures in the world, and explore how a dome that is still standing. But consider this before we continue. If Roman concrete could last 2,000 years, what are we building today that will outlast our own century? You step inside. It's quiet, cold, and massive. The sound of your footsteps disappears into the air above. Still intact after nearly 2,000 years. No steel, no plastic. It is one of the most studied structures in architectural history, not because it's the most beautiful or ornate, but because it shouldn't exist. Collapsed centuries ago, and yet it hasn't. Because of Roman concrete. Let's unravel the dome from the top. DOWNI. The eye of the storm. At the very center of the dome is the oculus, an open hole, nearly 30 feet across, that lets in light, rain, and silence. It seems like a flaw at first. Why leave a gaping hole in the middle of your ceiling? But the oculus is the key. It reduces stress at the most dangerous point, the center. Solid concrete would have been too heavy. The opening eases the load on the structure and directs weight along the rest of the dome's curve, and let the water drain into underground pipes carved directly into the foundation. Even the flaws were engineered. And this leads us to the real question. How did they pour a dome this massive, over 140 feet across, without modern machinery? Concrete, like a layer cake. Roman builders didn't use the same mix throughout the dome. Instead, they poured it in rings, starting from the base and moving upward in stages. At the bottom, the concrete was mixed with heavy volcanic stones, like basalt for strength. Eventually pumice, which is porous and nearly floats in water. This wasn't just clever, it was essential. But with the gradual lightening of materials, the structure remained stable and lighter at the top, like a mountain turned upside down. It up in baskets, carefully, layer by layer, over months or even years. You don't get second chances. But the Romans had done this before, on smaller scales. Sand, they had learned to listen to the material. They were not guessing. They were practicing. 3. The rotunda, a concrete drum that holds it all. The dome doesn't rest on thin columns or metal frames. It sits atop a rotunda, giant circular wall over 20 feet thick in places. It has relieving arches, embedded columns, and hidden voids, each calculated to redirect weight and channel stress toward the ground. Balloon. And all of this is still standing, without reinforcement, without repair cranes. The Pantheon has endured earthquakes, floods, and invasions, and it was allowed to settle naturally over time. It's not overbuilt. It's wise. For the unknown builders, we often credit the Pantheon to Hadrian. The original structure was built under Marcus Agrippa, general, around 27 BCE, but it burned down twice. First in 80 CE, again in 110. Hadrian, known for his deep love of architecture, likely entrusted the reconstruction to an elite team of imperial engineers, possibly led by Apollodorus of Damascus. Regardless, we don't know who actually poured the concrete, who hauled the stone, or who climbed the wooden scaffolding in the summer sun to smooth the inner vault. Their names are not recorded. There are no inscriptions, no memorials. There is a kind of poetic silence in that the interior illusion when you stand inside the Pantheon. The dome looks like a perfect half-sphere, but that's a trick of proportion. In reality, the dome's curve is slightly flattened, and the floor is slightly convex to help with water drainage. Even the decorative features serve structural purposes. The coffers, those sunken panels in the ceiling aren't just beautiful, they reduce weight. Each panel carved out of the concrete mass lightens the load, subtly shifting balance. Roman design was never just aesthetic. It was always functional beauty. They didn't waste space. They didn't chase innovation for its own sake. They observed, they revised, they built, forgotten for 1,000 years after the fall of Rome. The Pantheon became a church. That's part of why it survived. Pagan temples were often stripped for parts, but a Christian designation helped protect it, though not completely. In the Middle Ages, bronze from the portico was removed. Marble was pilfered, statues vanished, but the dome stayed. For centuries, the secret of its concrete was forgotten. Builders turned back to stone and brick. Mortar weakened. New concrete techniques emerge, but none as durable. Begun to relearn what the Romans knew, and it turns out they weren't using a better cement. They were using a better process. Longer curing, local materials. Falling short today, architects marvel at Roman concrete. We know the recipe: lime, pozzolana, water, aggregate. But we struggle with the patience. Roman concrete took months or years to cure and cracks the surrounding material. Roman concrete, unreinforced, has no internal rust. That's part of why it lasts. Some have even proposed using it on Mars, where steel rebar won't work and volcanic ash is plentiful. The Romans may have unknowingly created the perfect space, concrete, ready for interplanetary use. 8. What they knew that we forgot. We often say Roman concrete was accidentally better, that they stumbled upon good chemistry, but that's not quite fair. The Romans observed how volcanic ash reacted with seawater. They watched which mixtures failed and which endured. They tested new ratios in new climates. They didn't have microscopes, but they had memory. They passed knowledge across generations of builders, without manuals, through labor, through repetition, through craft. It was grown. The final thought. So now, when you hear someone talk about Roman engineering, try not to picture military roads or towering aqueducts. Picture a wall, a dock, a cistern, a bath. Picture a dome with a hole in the middle that still hasn't fallen. And remember, the secret wasn't a magic ingredient. It was time. Time to mix, time to wait, time to learn from failure. A kind of slow, dusty wisdom set in stone. This is a Roman kitchen where you are standing. It's a small room in a beach factory, not a grand palace with marble floors. The air has a strong tang from the salt, brine, and decomposing fish, sweating in the sun. Earthen amphorae are stacked to the ceiling in the corner. In a low basin, a thick, seething mass is stirred with a wooden paddle. It's hot, smells bad, and ferments vigorously. This is garum, the most valued condiment in Rome. A sauce made from fish, a high-end item, a medication, an essential. But flavor isn't the only reason we're here. We're here because it's possible that this disgusting beverage contributed to Roman construction's tenacity in an unexpected way. Isn't that odd? That the strength of walls might have been enhanced by a table sauce? This section will examine the ways in which Roman concrete and the manufacture, exporting, and storage of garum interacted. We'll begin by discussing the sauce itself, including its composition and manufacturing process. Before tracing its history through warehouses, amphorae, and the odd instance of leftover fish sauce contaminating mortar, let's start with the source of the odor. What was going on? In order to make garum, small, oily fish, such as sardines, mackerel, and anchovies, were layered with salt in vast open vats and let to ferment for months in the sun. This produced a strong, amber-colored liquid that was high in glutamates and resembled contemporary Southeast Asian fish sauces like nwok mam or nam pla. However, garum was more than just a food item. It was also a representation of wealth, prestige, and royal flavor. Garum came in many grades. Elites were the only ones allowed to use the premium variety. Garum, sociorum, animals, and slaves were fed the lesser grades, such as Elec, from the coast of Iberia to the Black Sea, and from Britain to Judea. Garum was exported across the empire. Garum-filled amphorae have been discovered in military forts, warehouses, and shipwrecks. Additionally, garum's storage infrastructure followed it everywhere. 2. The amphorae of garum. Each drop of garum needed its own container. These were not merely barrels or jars. Rather, they were specialist amphorae, made to carry an acidic, greasy, and salty material for extended periods of time. Large-scale garum manufacturers in Spain and North Africa started surrounding their workshops, and occasionally the amphorae themselves with concrete basins in the 1st century CE, although Roman amphorae were still mostly composed of clay. This is when the exciting part begins. Garum has to be fermented in impermeable vats. Ordinary mortar would be destroyed by salt and fish oils. Thus, manufacturers of garum started experimenting with waterproof plasters that included and occasionally organic leftovers from the fish sauce. Garum has been found inside basins made of Roman concrete, not stone or clay. According to recent archaeological research conducted at locations like Belo Claudia on the Spanish coast. Because of this, manufacturers of garum were depending on concrete to store their most valuable product. Why? Because concrete was faster to build, easier to clean, and, when mixed properly, extremely resistant to rot. Additionally, the garum itself may have occasionally been mixed up, as we shall see. 3. The unintentional supplement. An unexpected finding was made in 2018 by academics examining Roman building materials from garum production sites. Some mortar samples contained organic constituents, proteins, fatty acids that were consistent with fermented fish. These substances might have resulted from intentionally mixing residual residues into the subsequent batch of mortar, or from vats that were not thoroughly cleaned. The outcome, the mortar, didn't look as porous. In some way, salt and oil had sealed the concrete, increasing its resistance to water seeping in. The matter is still up for debate. According to some academics, the fish traces are pollutants rather than additions. Others think they are an example of a local innovation that was sparked by a real-world need. In any case, it implies that Roman construction workers were modifying their materials according to regional industries. In this instance, they were using their lunch scraps to create 4. The warehouses that had a dinner smell. Warehouses, known as horia, were long, dark structures used to hold amphorae until they were sent, and they were found where garum was. These buildings' flooring were frequently lined with concrete, which in some areas, particularly those close to areas that produced garum, was extremely resistant to salt corrosion. This is not an accident. Numerous concrete floors of Ostia, Rome's historic port city, have withstood centuries of exposure to water. Some even exhibit purposeful grading, with a modest slope to aid in runoff and spills. These garum warehouses, concrete frequently, had a high pozzolanic index, indicating that builders were employing marine concrete techniques for storage as well as harbors. Remind yourself that materials come after commerce. Stronger binders, tighter joints, and better curing were among the techniques builders took from harbor construction when the fish sauce industry demanded better floors, all in an effort to prevent product leaks, or maybe to prevent the odor from escaping. Trade, fishing, and technique spread. The garum trade was a global enterprise rather than a regional one. Building techniques for storing garum expanded along with it. In Roman Gaul, for instance, some inland garum markets employed cisterns and vats based after North African designs, rounded, concrete-lined, shallow ponds with sloped bottoms. These designs are traceable via trade channels, construction expertise, such as which aggregates held up better, which lime-to-wash ratios resisted the fish oil, and how long to let a vat sit before it could be securely filled. From the shore to the interior, it wasn't really scientific, it was a small-scale innovation. One builder reports less vat leakage. His method is imitated by another. A regional standard develops over time. In this sense, fish sauce served as a catalyst for building knowledge. Integration's boring genius, the notion that something as commonplace and, to be honest, repulsive as fermented fish might have an impact on imperial engineering may seem ridiculous to you. However, this is the exact reason why Roman history endures so well. It's not the victories or temples. It was the way that everything in life was interconnected. Architecture is fueled by industry. Infrastructure was affected by cuisine. Transport was determined by taste. There was no waste. Garum wasn't merely consumed. In some areas, it even influenced the chemistry of concrete, as well as trade, labor, and storage. What about the builders? The luxury of specialization was not available to them. A mason may spend a month on a fish vat, a month on a pier, and a third month on the floor of a villa. With them came the flow of knowledge, slowly, not a word. And concrete survived as a result of that flow and that common sense. 7. Things we're still discovering. The connection between old concrete and organic compounds is currently being discovered. Would garum or its byproducts have improved workability by acting as a primitive plasticizer? Were the pores sealed by the oils? Did some builders take advantage of this knowledge? Was everything an accident, or what? In an attempt to comprehend what the Romans never recorded, researchers are now reproducing old recipes using fish oil, animal fats, and even seawater. The fact is that Rome did not record its greatest concrete. Industrial byproducts are hardly mentioned in our primary source, Vitruvius. The trade secrets were not documented. They were used, instructed. Again, the final question, therefore, don't just see marble and emperors when you picture a Roman ruin. Think about fish sauce. Consider the dock worker who, in between loads of amphorae, agitated a concrete basin. Consider the builder who unintentionally strengthened his mortar mix by scraping fish remains into it out of need or laziness. Consider the vats whose recipes were outlasted. And consider this: how many of the greatest concepts in history were unintentionally found and never documented. You are traversing an abandoned Roman fish processing facility. The whitewashed walls are baked by the Mediterranean heat. Long since gone, the odor still appears to permeate the stone. A concrete vate's rim is rough, pitted, and surprisingly intact when you run your palm down it. There once was a garum factory here, one of several hundred found in southern Italy, North Africa, and the coast of Spain. Millions of liters of fish sauce were transported from this location to provide Rome's banquets, troops, and marketplaces. A silent transformation in Roman infrastructure, however, lies behind the commerce and the smell. Engineers were compelled by the demands of the garum trade to modify their designs, try out new materials, and reconsider the potential of concrete. We continue that change in this part. Vaults from vats, from vast coastal shipping hubs to fish producers, a tale of exporters, amphorae packers, and the covert dissemination of one of the empire's most underappreciated inventions. Not of emperors. Constructing the stomach of the empire, garum was more than simply sustenance. By the 1st century CE, it was a commodity, a good one. Rome had an insatiable desire. Garum was applied on almost everything in wealthy households. Large supplies were required by the military to season their diets high in grains. Additionally, it was a shelf-stable source of umami flavor that cities with diverse populations relied on. Production had to scale as a result. Garum could no longer be manufactured in shacks by the sea or in backyard pits. It needed specialized infrastructure, including port facilities, drainage systems, amphora kilns, and factories with dozens of fermentation vats. And concrete was necessary for all of this. Concrete that could withstand the extreme Mediterranean heat, acidic fish residue, and corrosion from salt water. Stone was unable to do it. The brick deteriorated. However, carefully mixed concrete survived along the Roman beaches. A sort of industrial armaments competition ensued. Below Claudia, a functional design case study. Claudia is located close to the Strait of Gibraltar in present-day Spain. One of the best preserved garum factories in antiquity has been discovered here by researchers. At its height, it featured more than 40 sizable fermentation vats, lined with pozzolanic concrete and carved or built into the ground. Not only is their quantity impressive, but so is their consistency. Every vat has the same dimensions, is tilted for effective drainage, and is attached to adjacent storage spaces and concrete walkways. A smooth, waterproof mortar covers a core of lime and volcanic ash used to build the walls. The important thing is that they are still watertight. Water put into some of these vats today will still hold, even after decades of neglect. The builders weren't fortunate for this. Deliberate proportions were employed. Studies reveal a significant proportion of siliceous volcanic sand in the mortar. indicating that they were carefully choosing materials rather than using local resources, and possibly importing ash to achieve the ideal combination, a facility that produces sauces and has its own concrete supply chain. 3. The odor management architecture. Garum had a foul odor. Romans acknowledged it as well. According to Seneca, a drop of garum has the ability to scorch everything it touches. Naturally, manufacturers created ingenious architectural solutions to manage contamination, discharge, and odor. Downwind of cities, a large number of factories were constructed. Vats could be routinely washed because some were situated close to natural seawater inlets. Crucially, many featured semi-open walls and vaulted ceilings to encourage airflow and lessen gas accumulation inside. Concrete was poured over temporary wooden formwork to create these vaults, which ranged in complexity from simple barrel shapes to more intricate groin forms. Once more, innovation was being driven by the fish trade. The development of industrial-grade Romans, concrete optimized for fish but soon employed for other applications as well, was prompted by the need for breathable, rinse, and expandable facilities. 4. Concrete kilns and amphorae production. A container was required for each liter of garum. Amphorae, standardized clay vessels that could be piled in ships and used again for trade, were the Roman answer. However, it wasn't simple to produce millions of amphorae. It needed cooling areas, drying racks, and kilns. Additionally, many of these kilns were built on or surrounded by concrete platforms in the garum regions of Tunisia and Spain. Why? Because other materials were deteriorated by heat, smoke, and clay dust. Once more, concrete provided durability, a miniaturized replica of the hypocaust systems used in Roman baths. Some garum workshops even employed tiny concrete tubes to more effectively distribute heat from furnaces. Knowledge, therefore, moved sideways, from homes to workplaces, from public bathing to the curing of fish sauce. Salts function in concrete chemistry, generally speaking. Salt is terrible for concrete. It promotes degradation, breaks down bonding, and corrodes metals. However, steel was absent from Roman concrete. Additionally, salt occasionally aided in the initiation of crystal forms deep inside the mortar when pozzolanic ash was utilized, particularly in humid or submerged conditions. Salt permeated the brine, the floors, and the air in garum industries. All day, workers trudged barefoot across concrete that was drenched with salt. Amphorae broke apart and spilled. Every surface was covered in dried brine, the finest Roman. Concrete did not crumble under this exposure. According to recent research, salt may have even accelerated the formation of uncommon mineral crystals, such as philipsite and altaburmorite, inside Roman mortar. These crystals grew stronger over time and were able to self-heal minor breaches. Put another way, the concrete might have benefited from the fish sauce's ability to age it via labor, memory, and material practice. How were concrete adaptations for fish sauce factories known to Roman builders? Not from books, not from scrolls. Through repetition, builders shifted from one job site to another. In Carthage, a laborer who constructed harbor docks in Puteoli might go on to construct vats. From master mason to apprentice, techniques are passed from one person to another. They observed what was effective. They witnessed the failure. Perhaps a builder noticed one day that some vats refuse to break as quickly as others when used with salted fish. Perhaps he scraped the leftovers from one batch into the next batch's mortar to save time, not to be smart. And gradually, after thousands of inconsequential choices, a superior concrete surfaced, a concrete with fish sauce, not eternal, not enchanted, simply straightforward, trustworthy. 7. Knowledge as a byproduct, an odd export. Rome exported more than simply garum. It exported a construction method. Roman builders and traders delivered tangible knowledge to Britain, Gaul, Egypt, and the Levant, along with amphorae and spices. Archaeologists now discover little garum factories or storage areas, each with regional variations in these remote regions of the empire. For instance, garum facilities were more enclosed in Britain, probably because of the country's cooler temperature. However, the concrete still exhibits the same waterproofing techniques and volcanic lime matrix. These were successful at times. At other times, they didn't work. We witness shabby repairs, broken tanks, and collapsing walls. However, the attempt was made in each instance. Garum generated demand. Experimentation was compelled by demand. Resilience was developed by experimentation. It wasn't lovely. It was not honorable. However, it persisted. 8. What we can learn from a vat. Remember this the next time you explore ruins. Whether in Rome or a sleepy coastal town, every imperial marvel was accompanied by 1,000 everyday necessities. Storage of food, drainage, resilience to fatigue, control of odor. And it's possible that garum, of all things, made Roman builders think more deeply. What can we do to prevent this from leaking? How do we create sturdy but quick structures? How can we prevent the walls from being eaten by salt? They responded with trowels rather than theories, using buckets, via mistakes and hardships. With perspiration and extended sun exposure, they left behind concrete that would outlast the fish. As a result, outlive the retailers, outlive the empire, for the simple reason that humans still needed food. The lengthy Roman workday is coming to an end. The contents of a vat, which is dark, viscous, and sharp-smelling, had just been drained. Amphorae wait in rows nearby to be waxed and carried to the port on donkeys. However, a mason gathers the scrap in one corner. The sauce doesn't appeal to him. He wants the fermented oils, dried salt, and leftover sludge that are clinging to the vat's sides. To repair a wall behind the amphora kiln, he will combine it with volcanic ash and lime. He is unaware that he is leaving archaeologists to solve a riddle. Furthermore, he has no idea that his patchwork will still remain intact centuries after the fall of the empire. In this last piece, we trace the long history of garum, including how it permeated building culture, outlasted its own recipes, and perhaps even helped the empire literally cement its place in history. Garum I waste as a source of materials. As we've seen so far, the manufacture of Roman fish sauce fueled demands for stronger concrete, better vats, and more effective patterns in architecture. However, the plot has one final twist: reusing waste. Large quantities of fish bones, intestines, salt slush, and briny sludge were produced by garum manufacturers. It was difficult to burn or decompose this stuff. It was salt-filled, thick, and sticky. Pigs were fed some of it, a portion was discarded into the ocean. However, builders started employing the trash as binder or filler in areas where volcanic ash was limited or time was of the essence. According to experimental archaeology, adding little amounts of fishy slurry to lime-based mortar helps reduce water infiltration, particularly in humid environments. Under the correct conditions, the salt may aid in triggering crystallization, while the oil appears to aid in sealing pores. Was this a common Roman custom? No. Was it captured on tape? No. 2. Was it, however, noticed and repeated? Most likely. Builders made do with what they had, particularly in the less affluent provinces that were distant from Rome's aristocratic architecture. That was garum waste, at times, compost-based concrete. 2. Fishy walls, oddly resilient nature, despite extensive exposure to salt. Archaeologists have found concrete walls in a number of Roman sites, most notably in southern Spain and North Africa, that exhibit exceptional endurance. These aren't imperial strongholds or harbor docks. They are cisterns, warehouses, and workshops, locations where garum was exchanged, stored, or stirred. Something strange is discovered by chemical analysis, organic signs baked into the mortar itself, such as residues of fatty substances, amino acids, and even fish proteins. This raised the question of whether these inclusions were deliberate or just the consequence of inadequate cleanliness. It appears that both are the answer. Where wastewater splashed over uncured concrete, it was pollution. In others, however, the combination appears overly steady and regular, as if it had been added and measured. It may have occurred to some builders that the stronger seal was created by the fouler mixture, and as soon as that pattern was noticed, storage platforms was one of its most underappreciated consequences. Traders would unload garum at temporary docks with concrete landing pads in places like Egypt and Roman Gaul. These were temporary piercings. They were modular slabs that were occasionally cured on the beach, poured into wooden frames, and then used again for several seasons. And you know what? Additionally, some of these portable pads have binders that contain residues of chemicals derived from fish. Not a lot, not consistently, but this implies that landing surfaces were occasionally patched or prepared on site using garum waste, which was plentiful at the trading sites. Concrete in Rome wasn't considered sacrosanct. It was flexible. Fascinatingly, the Romans showed no pride in their invention. Poems about mortar made of fish have not survived. No amphora holler statues. All that was fused into the floor were footprints, fissures, and the occasional fishbone. It was unimpressive, so history buried it. However, it was successful. For institutional memory, the journey from garum to guilds. How then was this knowledge transmitted? There were no engineering schools in Rome in the contemporary sense. Builder, crushed ceramics could be used as aggregate in Carthage. In areas that produced garum, this was not codified. However, it was instructed. We know this because building styles persisted even after garum lost popularity. Sloped fermentation vats and lime ash mortar were still employed by builders to preserve vinegar, olives, and anchovy paste in medieval Spain and Sicily centuries later. Garum vanished. Its containers survived. After the collapse, concrete. The garum commerce collapsed together with the fall of Rome. Ships with rows of amphorae filled with sauce no longer sailed every day. Factories close. The vats dried up. They were sometimes filled with rubbish or turned into wells. The concrete, however, held up. Old garum vats were converted into fish ponds, wine presses, or cisterns in places like southern Italy and Tunisia. Despite changes in the soil, despite generations of disregard, that has an understated sense of success. A rot-born material designed to smell, constructed to contain saucepo, comes more durable than the empire that produced it. As a wall that still doesn't leak, not as a ruin of splendor, not just for appreciation, but also for solutions. Why did it repair itself? How did it withstand the attack of salt, lime mortar, the possibility of fish waste in bioconcrete, particularly for low-cost or underwater construction, has been investigated by others. The outcomes are encouraging. By using solely the waste from their own food systems, it turns out that the ancients may have discovered low carbon, durable, biologically active concrete, a lesson to be remembered or rediscovering. Millions of them were produced, used just once, and then frequently thrown away. A lot of them ended up in shipwrecks. Others were recycled into concrete wall reinforcement, road foundations, and floors. The shards of smashed amphorae were actually blended into mortar by some Roman architects, who utilized them as an ideal aggregate because they were robust, porous, and slightly absorbent. The garum container thus served as the foundation for Roman concrete. Mouths were fed by the sauce. Cities were fed by its jars, and the cycle went on. A concluding thought: Rome was great, but it wasn't made of marble or gold. Vats were used to blend it, hauled in pails, patched next to fish bones, poured next to garbage piles, and stirred next to docks. Garum was repulsive. It was unavoidable. It was the epitome of Roman life, untidy, pragmatic, odorous, and subtly clever. And if you want to know how Rome created long-lasting goods, the fish must be followed. It starts with dust. Not the kind you brush off a table, but the kind that reshaped an empire. Light gray, almost pink, carried on the wind, swept from the flanks of ancient volcanoes, crushed, ground, and stirred with water. You might walk past it today and never know you're seeing the bones of a Roman house. This is volcanic ash specifically, the ash the Romans called pulvis putillanus, or pozzolana, named after the region near Puteoli, modern Poziolis. Fine powder became one of the most important building materials in the ancient world. It made walls stronger, cement last longer, and structures stand straighter through centuries of weather, quakes, and time. But it didn't begin in palaces or temples. It began in ordinary homes, in kitchens, storerooms, farmsteads, and rental flats. Places where people lived, washed, argued, and cooked lentils. And it was here, in the hum of daily life, that volcanic ash quietly transformed Roman construction. This is the story of how Rome's most unassuming ingredients seeped into the walls of homes, and how, in doing so, it helped the empire stand. Before Pozzolana, a world of weak mortar. To understand the Roman Revolution, we need to rewind. Before Pozzolana, ancient builders relied on lime-based mortar, made by burning limestone and mixing the powder with water. When exposed to air, the mixture hardened as it absorbed carbon dioxide. This process was slow and unstable. The resulting mortars were vulnerable to moisture, cracked easily, and lacked cohesion. Homes built with these early mortar needed constant repair. Roof leaks turned walls into mush. Foundations had to be thick and redundant. Builders compensated with over-engineering rather than chemical advantage. Enter pozzolana. When Romans began mixing this volcanic ash into their lime, something changed. The mortar no longer just hardened, it reacted. The chemical process, known today as a pozzolanic reaction, caused calcium silicate hydrates to form strong, stable, and water-resistant. The ash made the concrete cure underwater and gave walls the ability to resist humidity, temperature, swings, and earthquakes. What had once been dust from a mountain became structural magic. 2. The ash beneath the floor in many modest Roman homes insula or apartment buildings. Builders began by laying a foundation of stone or rubble. Then came a leveling layer, a rough concrete called rudis, often mixed with coarse gravel and bits of broken pottery. But in regions near volcanic activity, Apple's Campania, parts of Sicily, the mix often included pozzolana ash. Sometimes, this inclusion was accidental. Local soil naturally contained the right ash. Other times, it was deliberate. Builders knew that pozzolana made the rudis layer firmer, especially in damp conditions. In Pompeii, for example, many homes had floors made of opus signinama, waterproof mortar of lime, ash, and crushed terracotta. These floors didn't just resist wear, they sealed in moisture, protecting the layers beneath, and they were beautiful. Red-pink from the pottery, smooth and cool underfoot. An unassuming display of Rome's mastery over materials. 3 walls that harden over time. The same principle applied to walls. Builders used concrete cores, known as opus cementissime, sandwiched between brick or stone facing. In wealthy homes, this might be hidden behind frescoes. In poorer homes, it was left bare or lime-washed. But what mattered was what was inside the mix. With pozzolana, Roman walls didn't just dry, they cured, slowly, silently, over months or years. As moisture entered the wall, the ash-lime reaction continued, filling microcracks, hardening the core. This is why many Roman walls are still standing today. Not because they were massive, but because they were chemically alive. Some builders even intentionally left walls damp for weeks, allowing the reaction to deepen. Plasterers learned to mist the surface before applying finishes. It wasn't superstition, it was science, practiced without equations. For ash, paint, and plaster inside the home, pozzolana also made its way into plaster and paint prep. Standard Roman wall plasters were made with slaked lime and sand. But when ash was added, the plaster became harder and more flexible, allowing for smoother painting surfaces, especially for some homes in Pompeii show evidence of layered plaster systems. A base of coarse lime-ash mortar, a finer intermediate coat, and a final polished surface, sometimes burnished with wax or oil. The ash helped these layers adhere to stone, resist cracking, and survive earthquakes. Even the pigments benefited. Mineral-based paints, mixed with a pozzolanic base, resisted fading better than those painted onto weak lime plaster alone. Ash wasn't just a hidden strength. It was the canvas of domestic life. A geography of dust. Pozzolana wasn't everywhere. Its best forms came from Campania, especially around Puteoli, and the volcanic plains near Vesuvius. Builders farther north or east had to import the ashaphon at great cost. This led to to regional disparities. A villa in Naples might survive 2,000 years, a house in Gaul, less likely. But even in distant provinces, some builders tried to imitate pozzolana, mixing crushed brick or tile into lime to mimic the ashes effect. These substitutes, called artificial pozzolans, worked well enough, especially in floors and plasters. This is one of Rome's quiet genius moves: decentralized material innovation. There was no empire-wide concrete standard, but there were shared principles carried by masons, builders, and veterans turned landowners. Everyone learned what held and what didn't. Vi. The insula problem. Most Romans didn't live in villas. They lived in insulae, apartment blocks of brick and concrete, stacked several stories high. These buildings had a problem: weight. The higher the floor, the cheaper the material. Ground floors were reserved for shops or wealthier tenants. The top floors were hot, leaky, and prone to collapse. Pozzolana offered a solution. By mixing ash into concrete floors and walls, builders could make lighter, stronger slabs. Some insulae even used concrete vaults between floors, curved structures that carried weight more efficiently than flat beams. Still, not all builders used pozzolana wisely. Many rushed the cure. Others skipped the ash entirely to save money. And some of those buildings collapsed. The Roman satirist Juvenal famously joked about buildings crumbling in the night, crushing the snoring tenant before he ever knows he's dead. But the ones that stood often had ashes in their bones. 7. Ash in the air, ash in the wall. There's a strange poetry to it. The same volcanic eruption that buried Pompeii in ash also provided the material that made its homes last. Archaeologists digging today often find walls still standing, rooms still painted, floors still sealed, preserved, not just by disaster, but by chemistry. Pozzolana didn't make homes luxurious, it made them resilient. It gave ordinary Romans, artisans, merchants, farmers the chance to live in buildings that withstood storms, tremors, and time. And because of that, we can still walk those halls today, still see the kitchens, still trace the outlines of everyday life. All because of a decision to add a little dust to the mix. Unresolved thought, so now you've seen the walls, the ones with ashes inside them. But what if the secret to Rome's most enduring structures wasn't just the ash, but the way they mixed it underwater? A trick not just of chemistry, but of marine design. A secret learned not in homes, but in harbors. Stand on the edge of a Roman harbor. Waves lap against crumbling blocks of ancient stone. Gulls circle overhead. And just below the surface, still visible in the clear Mediterranean water, you see them. Massive, submerged structures, some half-buried in silt, others stubbornly intact. The answer lies in ashes, again not sprinkled in walls or floors, but mixed into cement and poured into the sea itself. This wasn't normal concrete. This was marine concrete, engineered by Romans to cure underwater, bond with salt, and grow stronger over time. In this section, we move from kitchens and homes to harbors and headlands, tracing the rise of the ash that builds beneath the waves. We'll look at how Roman builders conquered the coast, turned dust into stone, and changed the literal boundaries of empire. What they discovered without modern chemistry still challenges, and the mixture dissolves. Even modern Portland cement struggles to survive in seawater without corrosion. But Roman engineers needed harbors, lots of them. The empire stretched across thousands of miles of coastline. Ships had to dock, trade had to flow. Protection from storms and pirates was essential. So how did they build breakwaters without modern forms, scaffolds, or underwater vacuum pumps? The answer was astonishingly simple. They used pozzolana, mixed it with lime and rubble, and poured it directly into the sea using wooden frames called casemates. Once inside, the ash-lime mixture reacted with seawater. Rome's accidental genius. Modern chemists now understand what the Romans stumbled upon. When volcanic ash is mixed with lime and exposed to water, especially salt water, it forms calcium-aluminum-silicate-hydrate, COSH, and other crystals. Like philipsite, these fill voids in the concrete, bind aggregate together, and grow stronger over time. What's more, Roman marine concrete is chemically self-healing. Small cracks allow water in, which triggers new reactions, which fill the cracks. Today, this process is being studied in cutting-edge, sustainable concrete projects. But Rome got there first, with no lab, no microscopes, no formal chemistry. They just saw that the mixture worked, and they kept using it. 3. Portus, Caesarea, and the concrete empire. Two of the greatest examples of Roman marine concrete are Portus, Italy, built as an extension of the port of Ostia. This vast, artificial harbor included curved breakwaters, lighthouses, and massive submerged foundations. Caesarea Maritima, Israel, constructed under Herod the Great, both used opus cementitium, the Roman term for concrete, a heavy dose of pozzolana, and a unique layering process. A box was built of wood, often open on one side. It was floated into position and partially sunk. Inside, a mix of lime, ash, and volcanic sand was poured in along with large stones for ballast. The ash-lime mixture reacted underwater, creating solid mass. Once cured, the box was removed or left to rot. The result, a concrete structure bonded to the seafloor. Astonishingly, the blocks laid at Caesarea are still intact while many modern seawalls have collapsed. 4. Lessons from the sea. What builders took inland, the techniques used at sea didn't stay at sea. Builders began applying marine concrete strategies to inland structures, in cisterns, baths, aqueducts, and foundations for large buildings. You see, even in cities, water was a threat. Groundwater, runoff, humidity could all ruin a poorly made wall. But marine concrete resisted water. Soon, Roman engineers were using seawater in inland mixes when possible, storing ash in dry vaults, guarded like a resource, importing pozzolana ash to regions that lacked it. Wealthy landowners might even build artificial fish ponds with marine concrete, mimicking harbors. The walls didn't leak. Marine construction methods became a mark of prestige and resilience. V-builders. Without blueprints, there's a striking thing about Roman harbor construction. There were no standardized measurements. Each site was different. Each team improvised. They didn't follow mathematical plans like modern engineers. A builder who had worked on a breakwater in Campania might later build a bathhouse in Gaul. He brought with him a mental recipe. 3 parts volcanic ash, 1 part slaked lime rubble as needed. Pour in stages, let the sea do the rest. No formulas, just a dusty thumb, a practiced eye, and a slow pour, and yet it worked. Vi Pozzolana's decline, a recipe forgotten after the fall of the Western Roman Empire. The mixing ratios weren't written down, were taught, not taught in scrolls. Many regions lacked access to proper volcanic ash. By the early Middle Ages, European builders had reverted to simpler lime mortar, weaker and slower to set. For centuries, the magic of Roman concrete, especially marine concrete, was lost. It wasn't until the 18th century that pozzolanic chemistry was re-examined, and even today, we haven't fully replicated the durability of those underwater Roman structures. Their strength came not just from ingredients, but from practical wisdom, timing, texture, patience. 7. Where the ash still holds today. You can visit ancient ports like Cosa. Some paths slope gently into the water. Others break through the tide like buried fangs, all made with ash. Scientists have sampled cores from these sites. Under microscopes, they find minerals still growing, binding, stiffening. One researcher described it as a living stone. Another simply said, "It's better than ours." You could call it primitive or ahead of its time, because while our modern concrete can last a century, but the connection remains. What started in kitchens and floors also built breakwaters and seawalls. It's the same dust, the same chemistry used for shelter and strategy, for walls and warships. The Romans didn't separate domestic and imperial innovation. They built one with the lessons of the other. And maybe that's why their concrete born from flame and dust has outlasted their gods, their emperors, and their histories. But what if ash was only one half of the secret? What if the real reason Roman concrete lasted so long wasn't just the ingredients, but the deliberate way they cured it over time? Not just what they built with, but how long they waited. In Campania, a Roman wall that was once a component of a long-forgotten villa still stands. Wild grass grows between the floor tiles, the roof is gone, and the frescoes are faded. However, upon closer inspection, the wall's oddly intact concrete core can be seen, firm, don't spall, don't crumble. If you tap it, it will ring. It has been curing for around 2 millennia. The statement isn't a metaphor. Chemistry is what that is. In this last part of the narrative, we pay more attention to what the Romans allowed to happen in their concrete than to what they put in it. How their constructions were gradually shaped by method, time, and wetness. How, rather than hurrying against nature's speed, they worked with it. Because sometimes crumbled tile, lime, or ash weren't the secret ingredient. It was patience at times. The prolonged recovery. Contemporary concrete hardens rapidly. One of its main selling factors is that after pouring and letting it sit for a day or two, it's ready to use. It supports weight in a week. It reaches its peak intensity after a month. Roman concrete, however, was distinct. Instead of setting, it changed, slowly, depending on how it was exposed to air, water, and environmental changes. This could take months, or even years. Furthermore, this was no coincidence. Roman builders knew their mixtures required time. It had to soak in that water. That strength did not appear sooner. In order to accommodate the chemistry, they modified their construction schedules. For weeks, walls remained unfinished. To encourage curing, cisterns were filled and drained several times. Particularly during dry seasons, vaults were lifted. Months later, builders came back to assess the structure's strength before adding weight. There were no lab reports available. However, they possessed generations of practical knowledge. To fulfill a quarterly deadline, they weren't pouring concrete. In an attempt to outlive themselves, they were pouring it, too. Using wetness as a tool in modern building, dampness is considered as an enemy. It weakens, mixes, slows drying, produces issues. Moisture, however, was a stimulant for the Romans. Water is necessary for the pozzolanic reaction between lime and volcanic ash to occur. Without it, the concrete merely dries like clay, but it starts to crystallize inside when exposed to sufficiently regulated water, either directly or through the air. This meant that the mix cured more thoroughly in damp settings. Over time, buried barriers grew stronger. Surprisingly, buildings near springs or rivers held up well. Roman architects also adopted this style after noticing it. Drainage systems in some houses directed just enough water toward the foundations. The purposeful sweating walls of public baths were composed of porous concrete, which drew steam into it. Opus signinum, the waterproof plaster used in aqueduct channels, didn't completely solidify until months of water flowed over it. There was no danger from water. It was a companion. 3. Planning for postponement. The Roman approach has a lovely humility about it. Instead of aiming for instant perfection, they constructed for settling. They made it possible for buildings to change. Floors sagged a little, as was to be expected. Over time, vaults flexed. Typical. Did the mortar fracture and then mend? Expected. Some structures were planned with sacrificial layers, plaster coats, or lime washes meant to collapse first, safeguarding the structural core. Others included lengthy curing channels that might assist reinforce lower layers by allowing lime-rich runoff from one vat to seep into the next. You can practically picture a Roman site manager saying, "Don't worry, it's not finished. Return the next season." 4. Waiting builders. Think about a Roman builder's life. He gets up early, combines ash and lime, adds debris, pours walls, then he pauses. He bides his time. He'll be back in a week, then a month, 3 months later. Then the wall solidifies from the inside out. Throughout that period, he checks it with his knuckle. The surface is scraped, nods. Then he builds the following level, and only then. This was not a case of laziness. It was craft. We often think of ancient builders as hastily completing their projects before the arrival of fire, pestilence, or war. More often than not, though, they were just awaiting the chemistry. They weren't constructing a vacation home. For millennia, they were constructing. V-Speed forgets this slowly accumulating knowledge eventually disappeared. When the West entered the early medieval era and Roman trade lines fell apart, builders were no longer able to equality, ash, systems of transportation, the cure, period, rather. They preferred surface plasters and quicklime, which dried quickly but were short-lived. Speed had become crucial by the 19th century, when modern cement was created. Fast setting times were required by factories. Cities craved skyscrapers. Bridges have due dates. However, they also made mistakes. Bridges fell, the walls were leaking, the floors were cracked, the patience had vanished. Heal theirself. The most intriguing outcome of this waiting was something that the Romans probably didn't fully comprehend, but they undoubtedly observed: concrete that can mend itself. As we have seen, over time, Minerals like philipsite and altabormorite have been found in Roman sea buildings. These minerals expand into microcracks and seal them shut, even millennia after they are poured on land-based walls and floors. However, the same thing occurs, albeit more slowly. Researchers discovered that tiny fissures in the concrete were partially filled with freshly formed crystals in one investigation of the ancient Roman walls in Ostia. These crystals took decades to create. The chemical makeup resembled that of contemporary attempts at self-healing concrete. The wall had time for it all. It's time to relax, to move, to respond. It's time to be more authentic. 7. The cure's legacy that has a noble and subdued quality. A wall composed of lime, ash, water, and crushed stone that grows stronger with time, not in big leaps, not in short spurts, but in gradual, undetectable increase. Roman houses were like that. Not palaces, not temples to the gods, only floors, walls, and arches that got better with time. We demolish structures now before they are 100 years old. Roman builders, however, poured their mixtures, knowing that they would never fully experience the power of their creations. That is faith in the procedure. That is the tangible manifestation of patience. 8. Standing still. Remember this. The next time you pass an old wall, a pink concrete floor mosaic, or a dilapidated sea pier that has withstood generations of waves, it's not only what they used, they allowed it to be that way. Allow it to respond. Let it go. Give it time to settle. Give it time to heal. The wall is ashes. The fissures are wet. Every stone has time. The Romans allowed their structures to develop into what they were, perhaps. This explains why some people are still standing, considering what would happen if we didn't race through the skyscrapers of today. What might we produce for future generations, not for ourselves? Ultimately, the strongest barriers weren't completed in a single day. They were fed water, covered with dust, and allowed to cure over time. There's something almost invisible about bricks. They're everywhere, underfoot, overhead, beside you, in alleyways, behind plastered walls. They're silent, passive, dull. Nobody visits Rome for the bricks. They come for the arches, the domes, the marble gods. But nearly every ancient structure, the palaces, the bathhouses, the tenements rests on clay baked into red, dusty rectangles. And at one point in Roman history, these humble bricks became taxable. That's when everything changed. In this story, we look not at monuments or emperors, but at the economics of red clay. How a seemingly minor tax reshaped construction, spurred bureaucracy, altered architecture, and even helped build the empire's record-keeping system. This is the story of how a dull material, when stamped and tracked, revealed a living history of cities, how and when they were built, and by whom. It begins not with marble or grandeur, but in muddy pits on the outskirts of Rome. The first, the age of unregulated clay before the tax. Brickmaking was a mostly local affair. Families or small workshops would dig clay, shape bricks by hand or with wooden molds, and dry them in the sun or fire them in small kilns. The process was messy, seasonal, and entirely manual, but it was also essential. Bricks were the default building material of the late Republic and early Empire, especially in Rome and other densely populated urban centers. Stone was expensive. Wood was a fire risk. Brick was cheap, sturdy, stackable, and easy to repair. Still, there was no regulation, no standard size, no accountability. Bricks varied wildly from one region to another, and even within the same city block, that is, until the imperial administration realized something important. You could tax bricks. They were visible, countable, produced in massive batches, and most importantly, they were needed by everyone. 2. The tax that marked a wall sometime in the 1st century. CE historians debate the exact date Rome began implementing a brick tax across the empire. The exact form of the tax varied. In some cases, it was a production tax. In others, it was a market sale duty or a kill license fee. But what unified them was one clever policy. Every brick had to be stamped. Stamped with the name of the manufacturer, the location of the kill, sometimes the year or reigning consul, and later, even the emperor's initials. At first, it was about enforcement. You couldn't collect a tax without knowing where the bricks came from, but soon, the stamped bricks became something more. They became a tool for tracking imperial growth. 3. A brick for every bureaucrat. The stamps, called opus figlinarum marks, turned bricks into paperwork. Suddenly, a brick wasn't just a brick, it was data. A wall of bricks in a public bath might contain hundreds of stamps. Scholars today use these to date the building, identify the supply chains, trace regional trade, discover which workshops were state-owned. For example, many bricks used in the baths of Caracalla bear the stamp OPSC, Officinae Prefecturae, Summi Consigliere, indicating they came from imperial workshops run under state control. Others have stamps that include slave names, showing that even enslaved laborers were assigned formal brickmaking roles, and their labor was recorded. A single wall could contain stamps from multiple regions, proving that bricks were being shipped across provinces, a staggering thought for such heavy or fragile cargo. 4. When architecture met accounting, the tax also changed how buildings were built. Before the tax, builders had flexibility. Shapes and sizes could vary. Molds were customized. But under imperial supervision, standard sizes were enforced mostly 1.5 Roman feet square, about 44 centimeters, or rectangular units, like bipedalous 2-foot bricks. These shapes became modular, meaning walls, vaults, and arches could be constructed faster. It's no coincidence that Rome's most ambitious public works, Hadrian's Wall, the markets of Trajan, the aqueducts and cisterns of North Africa, date from this period of brick standardization. The brick tax unintentionally caused a boom in efficient building. The state made more money. Builders saved labor. Cities grew faster. Red clay became currency. Brick kilns as industrial powerhouses. The regulation also reshaped the brickmakers themselves. Before the tax, brickmaking was low-status work, but as demand grew and stamps became proof of legitimacies, some families and freedmen built brick empires. Entire regions near Rome, such as Trastevere and Ostia, were home to massive kill complexes, some producing millions of bricks per year. These weren't artisanal workshops. They were proto-factories, with clay quarries, mold stations, drying fields, kilns that fired thousands of bricks at once. Slave or freedman labor under tight schedules. Some workshops were patroon, others were owned by wealthy senatorial families, who leased their bricks to contractors and made fortunes off imperial contracts. Brick production became an industry, an identity, a way to climb the ladder of Roman power. Vi. Hidden histories in red dust today. Archaeologists scour ruined buildings for brick stamps. A single stamp might seem unimportant, but grouped together, they tell a story: where the clay came from, who owned the kiln, what year the building was made, whether it was public, private, or imperial in some cases. Historians have redated major buildings based entirely on brick stamps, not coins, not inscriptions, but patterns in fired clay. Entire imperial timelines have shifted because someone, 1,900 years ago, pressed a wooden stamp into wet mud. And what's more incredible is this: even when stamps wore off, the bricks still told a story through shape, texture, clay composition, and firing style. Every brick has fingerprints. 7. Red clay in the provinces. The tax wasn't just enforced in Rome. Across the empire, brick stamps appear from Britain to Egypt, Dacia to Tunisia, but the styles vary. In some provinces, bricks were rarely stamped, suggesting local governors took liberties. In others, imperial control was tight, especially in military zones, where forts and walls required strict documentation. In fact, the bricks of Hadrian's Wall contain some of the most detailed stamps in the empire, naming the legion that produced the brick, the unit that built the structure, even the batch number. In some cases, this was Roman efficiency, logistics, bureaucracy, and military strength, all fired into a red tile. But not everyone welcomed this dusty bookkeeping. Some brickmakers resented the tax, some cheated the stamps, some faked kiln names, and in one case, a group of workers may have revolted over clay. By the early 2nd century CE, brickmaking in the Roman Empire had become a highly regulated industry. It wasn't just about drying mud in the sun anymore. It was about permits, stamps, kiln records, licensing fees. You couldn't fire a batch of bricks without someone somewhere wanting a cut. The empire, in its love of order, had turned one of the oldest building crafts into a bureaucratic machine. But wherever there are rules, there are rule breakers. In this section, we explore the quieter side of Roman resistance, not with swords or riots, but with forged stamps, misreported batches, and underground kilns. We'll also look at how state control of red clay sparked class tensions, and how those tensions left their marks, sometimes literally, in the walls of cities. The burden of the stamp, officially. The stamped brick system was simple. A brickmaker, registered with local authorities or the imperial office. Each kiln was issued a wooden or bronze stamp with identifying text. The stamp had to be pressed into every brick made. When bricks were sold, a tax was paid based on quantity, location, or purpose. In practice, this system was a mess. Stamps broke. Brickmakers changed locations. Workers forgot or ignored protocol. And worst of all, taxes rose. By the mid-2nd century, wealthy owners could absorb the fees, but freedmen, independent laborers, and non-citizen contractors, they struggled. Some began cutting corners. Others got creative. 2. The rise of fake stamps. It started with forgery. If you had access to a kiln, you could produce bricks, but if you didn't have an official stamp, they couldn't be sold legally. So some workshops began to carve their own stamps, imitations of legitimate ones, complete with fake names and imperial seals. Others reused old stamps from previous owners, knowing the bureaucracy was too slow to catch up. A few even created phantom workshops, stamping bricks with names that didn't exist, then selling them at a discount under the table. Archaeologists have found bricks with blurred or backward letters, inconsistent styles on the same batch stamps. From defunct families used decades after they disappeared, misspellings likely made by illiterate forgers, copying from memory. In short, a brick could lie, and often it did. 3. Underground kilns and hidden fields. Forgery wasn't the only trick. Some producers simply worked in secret. They built illegal kilns outside city limits, often in forests, abandoned quarries, or valleys near clay deposits. There, away from tax collectors, they fired bricks by night, unstamped and unregulated. These black market bricks were cheaper and often lower quality, but they were snapped up by poor families building rural homes, minor landlords expanding rental units, private shops, and storage depots. Even government projects might use them knowingly or not when budgets got tight. In one rural villa excavation outside Ravenna, nearly 60% of the bricks had no stamps at all, and those that were stamped had marks linked to unrecorded workshops, suggesting parallel supply chains hidden from official eyes. 4. Penalties and inspectors. The empire tried to fight back. Records from imperial edicts and building contracts refer to inspectors, curatores, figlenarum, who were sent to check kilns and audit production. Penalties for tax evasion included fines, seizure of materials, loss of license, in some cases even enslavement or branding for repeat offenders, but enforcement was patchy. Some provinces were so vast, terrain so rugged, that monitoring every kill was impossible. And in cities like Ostia and Puteoli, inspectors sometimes turned a blind eye to off-books butchers, as long as their cut was delivered. The empire had built a brick bureaucracy, but its cracks were showing. Class tensions in clay. What began as a building tax slowly became a symbol of class tension. For wealthy families who owned large kilns, the tax was just another ledger entry. In fact, many embraced it, seeing the stamp as a mark of prestige. Their names spread across Rome, one wall at a time. But for small-time producers, especially freedmen, artisans, and provincials, the stamp was a barrier. They couldn't afford the tax, couldn't afford to bribe officials, couldn't afford to be caught. Some responded by carving hidden messages into bricks, names scratched hastily in corners, pleas for fairness, crude symbols of resistance chains, broken tools, cracked letters. One brick found near Cumy bears a faint mark, non est iustum, it is not fair. The wall that brick supported, a public latrine, legal loopholes and brick brokers. Some clever minds found legal ways around the tax. A new profession emerged, the brick broker. Brokers would buy large quantities of stamped bricks from registered kilns, then resell them at a markup to builders. Some even leased stamps to small kiln owners for short-term use. Others opened secondary market skill sites where bricks were pressed but fired elsewhere. Technically legal, but practically impossible to track. This blurred the lines between official and underground production. A brick might be made in Kill A, stamped with Kill B's seal, fired in Kill C, sold under Broker D's license, and by the time it reached a wall in some Roman town, nobody really knew where it came from. The empire's need for control had created a maze, and inside that maze, clay flowed freely. When a brick sparked a riot, there's one peculiar case, half history, half mystery, that suggests the brick tax may have even sparked open rebellion. In the city of Florentia, modern Florence, a 3rd century text refers to a riot among Claimon tumultus inter lutarios, in which several buildings were burned and a tax collector was killed. The details are sparse, but archaeological evidence shows dozens of kilns abandoned around that time, and bricks from that period begin to lack stamps entirely. Some scholars believe this was a localized revolt against the brick tax, possibly spurred by rising rates or unfair inspections. It didn't last. Order was restored, but the silence in the records speaks volumes. Even something as small as a brickwin tied to survival could ignite rebellion. But in the end, stamped bricks weren't just used for control. They were also used for legacy. Some emperors began using custom brick stamps, not for taxation. Why would a ruler care about stamping his name into wet clay? There were numerous ways for a Roman emperor to declare his dominance. He was a coin minter, build statues, requests poems, embellish cutlery. However, another technique more straightforward, more robust, and far more popular had joined the list by the middle of the 2nd century CE, stamping his name into bricks. Bricks, indeed. Rectangles that were used throughout the empire and produced in state-run kilns. What started out as a tracking and tax tool has evolved into a subtle yet effective propaganda tool. Walls are more durable than coins. Additionally, if baked correctly, a name stamped into clay can endure for 2,000 years, as well as to record ambition, form memory, and leave a mark of their identity that can still be seen in ruins today. Political messaging and imperial stamps, the first brick stamps, were useful. They contained batch, information, dates, and kill names. However, they developed a new personality under emperors such as Hadrian, Antoninus, Pius, and Septimius Severus. Bricks now bore emperors' abbreviated names, honorifics, and titles, defy, etc. Dates associated with periods of imperialism, sometimes even monograms or emblems. This wasn't just about taxation. It has to do with being there. Bathhouse in North Africa, or on a cistern in Syria. Rome is this structure, as symbols of civilization. Embedded in the very framework of the empire, the bricks turned into messengers of power. Two constructors, who made theirself eternal bricks, were not just stamped for pride by rulers. Stamps were used by brickmakers, particularly those who were wealthy, to designate the cities they supplied. A freedman in Rome. Almost all of the public structures that used his bricks have the following stamps. FIGLL, Teddy, vital, a humble name, hammered into red clay. Not that he was a senator, he was not an army leader. However, his initials are still visible on the walls of bathhouses, homes, and marketplaces. Heart, its ruins, its dusties, loaded with these messages. The theater of Marcellus and the markets of Trajan closely. Individual producers. Imperial kilns units at the provincial level. The engineering corps of the army. Building renovations are frequently dated by these stamps with the same accuracy as the building's foundations. Caused experts to recalculate the estimated construction date of a large public bath by 75 years. Additionally, because Roman buildings frequently reuse brick, those markings turn into historical breadcrumbs that let historians follow a single brick's existence through several decades and places. 4. Transitioning from pagan to Christian. However, its meaning evolved. Simple crosses or a chiro are examples of Christian symbols that were applied to some late period stamps after post-production or reuse. According to one hypothesis, when pagan temple bricks were converted into churches, they were occasionally scuffed with crosses as a means of spiritual purification. This leads to an interesting irony. Bricks that were first imprinted in honor ended up being incorporated into basilicas, honoring the exact religion they attempted to stifle. It appears that history is replete of reinterpreted meanings. The traveling bricks. Not every brick remained in the area. Stamped bricks have been discovered hundreds of miles away from their original kill. Dalmatian villas use bricks from Campanian kilns. This unveils a secret map of brick commerce lines throughout the empire, not just within towns. Not every clay that was available was being used by builders. They were importing quality, selecting bricks according to reputation, area, or stamp. For major imperial projects, bricks were occasionally even specially ordered. They were pre-shaped, pre-stamped, and sent in enormous quantities to far-off provinces, all made possible by heat, water, and dust. Wall names are printed on contracts, plaques, and web pages in the modern world. At the time the brick was stamped, some were probably slaves. However, their names endure, turned to terracotta by burning, impervious to rot, flood, and fire. And you're looking at more than just architecture when you see a Roman wall, especially one that hasn't collapsed in 2,000 years. The tax. Let's start with a tax, which is where it all started. A straightforward rule. Put a stamp on each brick. It was a bureaucratic choice at the time, involving the need to supervise output, maintain standards, and raise cash. Rome, however, unintentionally produced a time machine in the process. Every block turned into a piece of a greater narrative, an indication of policy, a rumor of commerce, an indication of urban growth, a name that held up in the face of destruction. Archaeologists now reconstruct timelines using bricks from destroyed temples or abandoned foundations. A conflict could be confirmed by a single stamped block. A historian might be contradicted by another. The only name that remains of a person who has been removed from all other records may appear on a third. All because the empire wanted some more money and someone had stamped clay. Concluding thoughts. Marble is more awe-inspiring than brick. They are humble, functional, not very noteworthy, but that's why they were so important. Rome didn't use stone or gold to construct its empire. It constructed walls with the expectation that they would last, fired in smoke, and formed mud by hand. And the names were still there in those walls, observing, waiting to be noticed again by someone like you. When you imagine ancient Rome, you might picture colosseums, chariots, togas in the sun. But beneath the marble, under the cobbled streets, Rome was full of water, quietly moving, waiting in darkness, trickling through lead-lined tunnels and terracotta drains. Before fountains splashed in plazas and bathhouses steamed with elegance, cisterns gathered every drop. This is not the dramatic story of aqueducts arching across valleys. It's the boring history, but essential one, of how Romans stored, diverted, and measured water for daily life. It is the story of the plumbing empire, brick-lined reservoirs, sweating vaults, clay pipes, and lead conduits that made urban survival possible. Rome was not Rome without water, and Rome's water was carefully engineered, quietly maintained, and deeply political. In this section, we focus on the cisterns, the buried bellies of the city that captured rain, regulated pressure, and held back thirst for thousands of years. Before the aqueducts came, Rome wasn't always a city of aqueducts. In its early days, before the Cloaca Maxima, before aqua apierumens relied on natural springs, wells, and most importantly, rainwater catchment. Rainwater was collected from roofs, channeled down terracotta gutters, and stored in underground cisterns. These early cisterns were lined with waterproof plaster opus signinum, sometimes built beneath homes or courtyards, covered with flat stone lids or grates to keep out debris, carefully isolated from sewage runoff. Each household managed its own supply. In dry months, families would ration water, carefully measuring daily use, sweeping dust off cistern lids, and praying for rain. These systems weren't luxurious, but they worked, too. The shape of thirst. Roman cisterns came in many forms, but the most common was the bell-shaped tank, a structure carved or built to narrow at the top and widen at the bottom, like an inverted flask. Why this shape? It reduced evaporation. It allowed debris to settle in lower corners. It created a sense of security, a literal belly holding the lifeblood of a home. Larger buildings and villas often had multiple cisterns, interconnected with a system of channels and overflow drains. In some cases, wealthy estates had entire basements dedicated to water storage, with complex vaulting and filtration pits. Even the most remote military forts had small bell cisterns buried near the cookhouse upon their only source of fresh water. To live in the Roman world was to live with limited water, and that made the cistern sacred. 3. Public thirst and private control. As cities expanded, so did water needs. Public baths, latrines, fountains, laundries required steady, controlled water. And while aqueducts eventually carried water into cities, those flows were often intermittent, seasonal, unreliable for high-pressure needs, so the state built public cisterns, too. These were enormous. Some held hundreds of thousands of liters, buried beneath forums, markets, and bathhouses. But water meant power, and cistern control often became political. Local magistrates were responsible for maintenance. Leaks, cracks, or theft could spark fines or worse. And in some cities, landlords controlled private cisterns in apartment blocks, charging tenants for access or priority. Water wasn't free, it was negotiated. Even in the dark, the cistern had rules. 4. Leaks and linings. A cistern was only as good as its lining. Romans used opus signinum, a mix of lime, crushed tile, and volcanic ash, to plaster the inside. This lining prevented leakage, inhibited bacterial growth, grew stronger with time, as minerals formed microcrystals within cracks. But if a cistern cracked or the lining failed, water could leak into the earth or worse, mix with sewage, creating foul, dangerous contamination. In fact, some of the earliest Roman building codes strictly regulated cistern placement. Some wealthier households lined their cisterns with marble panels or bronze sheets. Though these were rare, most relied on the quiet labor of lime, ash, and patience. Just like the bricks, these cisterns were designed to last centuries, and some have cisterns in crisis. During times of siege or drought, cisterns became crucial defenses. In the siege of Masada, Herodian engineers had built massive stepped cisterns into the cliffs, collecting rare desert rainfall. These cisterns were why the rebels could hold out for months. In Pompeii, when Vesuvius struck, many households turned first to their cisterns, drawing last water before the ash sealed them shut. Even during plagues, when fountains were abandoned and aqueducts broke down, cisterns, if covered, remained safe. To own a full cistern was to own time, days or weeks of survival hidden beneath your feet. It's no wonder cisterns appear so often in Roman inscriptions and legal codes. They were not decorative, they were life support. The sound of water. In the dark, imagine the silence inside a Roman cistern. You descend narrow stone stairs. Your torch flickers. The air is cool, wet, heavy. You hear the slow drip of water falling from a pipe or a cracked ceiling vault. The sound echoes off plaster walls. You kneel, lower a clay jug, pull it up, heavy and sloshing. You leave. The water waits again, motionless in the dark. Thousands of Romans had this experience daily. They didn't romanticize it. It was routine, unseen, boring. But without it, there is no Rome, no empire, no civilization, only thirst, unresolved thought. But water is rarely content to sit still. Once cisterns were full, the Romans had to find ways to move it up, down, across, and into homes. And that meant lead pipes. What did the Romans know about lead, and how did they use it to build a plumbing empire beneath the city? If cisterns were the bellies of Roman cities, and like veins, they carried life, but also risk. In this section, we explore the rise of Roman plumbing, how water moved from distant mountains to fountains, homes, and bathhouses through a complex, often overlooked network of pipes. But we'll also look at lead's convenience, its toxicity, and the ongoing debate about whether Rome poisoned itself, drop by drop, in its pursuit of civilized life. This is not the story of waterfalls or aqueduct archesites, the story of the plumbing nobody saw, beneath floorboards and behind walls, where pressure, pipes, and politics quietly pulsed together. From cistern to spout, once water was gathered, whether by rain, well, or aqueduct, it had to be distributed. Early Roman households used bucketon jug systems, draw water from a cistern, carry it to the kitchen, bathe in a basin. But as infrastructure improved, wealthier homes and public buildings began to install piped water. High-pressure use, simple gravity-fed systems, no pumps, just slope and weight in most cases. Water entered a building into a header tank, often stone or bronze, from which smaller pipes branched out to taps, calices, fountains, or baths. It wasn't pressurized by today's standards, but it worked. Water flowed downhill, aided by slope and siphon. The Romans didn't invent pressure plumbing. They invented dependable plumbing, the empire's favorite metal. So why lead? It was abundant, malleable, durable, waterproof, easily soldered resistant. Corrosion lead could be rolled into sheets, shaped into tubes, and joined with molten metal or bronze fittings. It was more expensive than clay, but far more adaptable and ideal for cities where it helped wash tombs or channel runoff. Some lead pipes were massive, up to 20 centimeters in diameter, and stamped with the name of the foundry or owner. Others were tiny, feeding single rooms or trickling water to indoor latrines. Instead, it was a patchwork, public mains branching off from aqueduct delivery points, literally controlled how much water one could receive. Want more water? Pay for a wider nozzle. And so, plumbing became class-based. Wealthy villas had ornate spigots, bronze taps, indoor baths. Poorer homes, buckets, and courtyards. Still, even modest apartments often had shared access to piped water at the building's base. For the first time in ancient history, cities had indoor plumbing, not universally, but consistently. For water theft and pipe politics, piped water also brought new crimes. Tapping into the wrong main line, widening your nozzle without a permit, or rerouting public supply to private homes were common offenses. Pliny the Younger, while overseeing Bithynia, wrote letters complaining of illegal spurs and pipe theft, sometimes requiring entire networks to be dug up and corrected. Rome had official inspectors curators, aquarum to monitor flow and usage. They kept records, measured pipe diameters, and enforced payment. Even water was taxed, and those taxes were embedded into the very metal. Many pipes are stamped with names, dates, or markings, proving legal ownership. A pipe, like a brick, was a receipt, visible proof that someone paid to be connected. The lead question now comes the uncomfortable part. Did Roman plumbing poison people? Infertility, cognitive decline. Modern critics, from 19th century physicians to 21st century historians, have suggested that widespread lead use may have contributed to Rome's decline, a slow mental erosion of its elite classes, sipping poisoned water from silver cups. Recent archaeological studies suggest hard water, rich in calcium and minerals, formed protective scale inside pipes. This mineral crust likely blocked much direct lead absorption, and flowing water didn't sit long enough in pipes to leach significant amounts. In short, the danger was real but possibly exaggerated. Lead poisoning likely occurred, but more from lead cookware, cosmetics, and wine additives, not water alone. Still, the plumbing system left behind a toxic legacy, a metal memory, preserved in ruins and reservoirs. The pipes that time forgot. Lead doesn't rot. Chemical insights into mineral content, water origin, and flow direction. In one notable case, pipes in ancient Londinium, London, still showed distinct ratios of Roman origin lead isotopes, allowing scientists to trace their source to Spanish mines used under Emperor Claudius. A pipe isn't just a tube, it's a timeline. 7. Plumbing as prestige. In the end, Roman pipes weren't just infrastructure, they were status. To have piped water was to have wealth. To control plumbing was to control hygiene, comfort, and public image. Even today, ruins of bathhouses, villas, a city's ability to flow water silently, predictably, and safely without anyone noticing, a mark of Rome's genius. Unresolved thought, but what happened when the water finally stopped, when the pipes dried and the fountains fell silent? What became of the infrastructure in the centuries after the empire collapsed? For ages, Roman cities were flooded, cisterns to baths, lead pipes to fountains, aqueduct arches to mountain springs. It all functioned silently, probably, day after day. After that, it didn't. Roman water infrastructure did not disappear all at once. It wasn't a massive flood or a dramatic act of sabotage. Rather, it was a protracted, sluggish forgetting, slow disintegration of habit and stone, of maintenance and knowledge. Pipes stopped flowing because no one was left to fix them, not because they broke. This last section examines what transpired with Rome's water systems following the fall throughout the old empire, not just in the capital. We'll look at abandoned buildings, recycled components, and the dim recollection of plumbing that once provided services to millions of people. We'll conclude by considering what it meant for a society to lose control over its water resources. The centrist long end. It took time for Rome to fall. Its plumbing didn't either. In many cities, water systems continued to work until the decline of the Western Roman Empire in the 4th and 5th centuries CE. Even into the early Middle Ages, Rome's public fountains were supplied by the Aqua Virgo aqueduct. Long after baths were abandoned, cisterns continued to be used. Although unevenly, pipes were still used to supply monasteries and mansions. However, problems had already started. Budgets for maintenance were drastically cut. Once educated in imperial academies, engineers and surveyors became increasingly scarce. Roads collapsed. Bridges over aqueducts collapsed and were left unfixed. Cities as a whole shrank. Gradually, gravity stopped providing what it used to. Broken arches, vandals, and war. A common fallacy is that Roman cities were crippled by the destruction of aqueducts by invading tribes. The truth is more nuanced. During the Gothic siege of Rome in 537 CE, the Ostrogoths blocked the aqueducts rather than destroying them. They utilized water as leverage because they understood its value. However, many aqueducts were already in poor condition prior to this. The system had been undermined by earthquakes, floods, and material theft. After a century of neglect, the Aqua Claudia, once a marvel of imperial Rome, went out of service. Additionally, the central authority required to coordinate extensive plumbing systems just vanished as the empire fell apart. 3. Silent fountains. The fountain, those open-mouthed spouts that continuously poured into marble basins, was the emblematic center of Roman water. They weren't only ornamental. For thousands of residents, they served as their main source of water, which was crucial in urban apartment complexes without private plumbing. These fountains dried up as aqueducts failed. Once resonating with the sound of water splashing, Rome became strangely quiet. The capital was referred to as a city of ghosts by travelers in the 8th and 9th centuries, with abandoned arches and barren basins overrun by flora and fauna. However, some water systems persisted despite the downturn. Originally constructed in 19 BCE, the Aqua Virgo continued to operate in part during the Middle Ages, supplying food for aristocratic homes and monasteries. Even with their cracks and patches, old water lines continued to seep into memory. 4. The development of buckets and wells. In the absence of running aqueducts, towns resorted to manual labor, wells, and springs. Rome excavated deeper wells in the Middle Ages. Old cisterns were utilized by monasteries. Lead pipes were occasionally taken from the ruins and melted to make utensils, statues, or church bells. Infrastructure no longer included plumbing. It was scrap. Additionally, the demand for extensive water infrastructure decreased as cities' populations shrank. Automation was replaced by manual haulage. Rain barrels were used in homes. The scent of the streets was stronger. The water's sound became infrequent. Systems that are forgotten, rediscovered. The Roman systems were rediscovered and studied by engineers during the Renaissance and Enlightenment centuries later. They were perplexed by inscriptions on lead pipes. Ignorant of Rome's proficiency with siphons and pressure balance, scholars argued about how water used to flow uphill. Popes and monarchs used repaired aqueducts, which were frequently constructed on top of ancient pathways, to commission new fountains in Rome. By the 17th century, inspired by the ancient Aqua Virgo, the Trevi Fountain was built in the 1730s. By that time, however, the information was incomplete. Once passed down through apprenticeships, guilds, and manuals, the live tradition of Roman plumbing was no longer practiced. All that was left was speculation. Lead, bricks, and flow archaeology. The ruins of the water system in ancient Rome are now dispersed and silent. Beneath London and Pompeii were lead pipes. In France, Spain, and Turkey, aqueduct piers soar across fields like broken teeth. By reconstructing flowcharts from these artifacts, archaeologists attempt to determine pressure gradients and pipe lengths using instruments that were never intended to last this long. Researchers continue to argue Rome's actual water consumption, whether or not lead actually caused widespread sickness, how many people lived outside of the system, and how frequently it failed. There are as many questions as there are answers amid the ruins. 7. The society that invented silence. Ultimately, Rome's water systems were the reason it did not endure. As long as its water systems lasted, Rome did too. Cities expanded, people bathed, and governments operated when water flowed silently, consistently, and imperceptibly. However, society became fragile when it failed, when the cisterns filled with dust, the pipes split, and the inspectors disappeared. A $50 million empire cannot exist without water, cannot exist without upkeep. Rome overlooked that, and history's silence replaced the quiet of dry fountains. Concluding thoughts today, it's simple to appreciate Roman plumbing, the arches, the inventiveness, the drive. Perhaps the more significant lesson, though, is not in what they constructed, but rather in how silently everything collapsed. A civilization is judged by the things it quietly upholds, such as safe streets, warm houses, and pure water, rather than by its monuments. And we seldom ever realize until it's too late, when those silent systems malfunctionally